Welcome to Module 4. The topic is going to be gravity and projectile motion and satellite motion. And notice the picture here on the screen. It's a picture of Isaac Newton. Now, we haven't talked about Isaac Newton since really Module 2 when we covered a lot of Newton's laws of motion. What I want you to think about is, first of all, how brilliant Newton was. Newton, legend has it, was sitting under an apple tree and saw an apple fall. And again, because he came up with the laws of motion, he knew that apples don't just fall because they want to. They are being forced to move. When you see something at rest, hanging in a tree, then all of a sudden, boom, it's falling toward the ground, you know a force is acting. And he then realized that that force was gravity, the force of the earth pulling on stuff. But he also had this much more significant observation that the same force that causes that apple to fall keeps that moon in motion as well. So he was able to extend this law of gravitation universally. He knew that all objects attract each other, and we're going to investigate that relationship during the course of this module. Okay, let's dive right in and introduce the law of universal gravitation. So the law of universal gravitation essentially just means that everything that has mass will attract other objects that have mass. And the relationship, or the way you can actually calculate the amount of force that something attracts something else with, is this kind of complicated mathematical equation. It says that the force of gravity is equal to a constant, we're going to talk about the constant here in a second, times the mass of one object times the mass of the other object. Then you have to divide by the distance between the two objects, and you have to square that distance. Now let's think about a force that we have talked about, a force of attraction that we've talked about. We have already talked about the fact that the Earth attracts us, human beings, with a force, and that force we call weight. In fact, we actually differentiated weight from mass, right? We had a weight. Weight is m times g, little g, what we call the acceleration due to gravity here on Earth. Notice, isn't that what the equation here on the left is also calculating? It's calculating the force of attraction between two objects. So notice that in the W equals mg case, we're specifically talking about the two objects being the Earth and a human being. So really, what we've done is we've used this equation on the right here, the W equals mg, is just a special case of the equation on the left. The equation on the left is much more general. You can have any two objects. In the case on the right, we're talking about two objects being the Earth and a human being. And the distance, of course, being the radius of the Earth. It's the distance between the person and the center of the Earth, which is about 4,000 miles. So if you plugged in those specific numbers, in this case, if we wanted to reduce the equation on the left to the equation on the right, we would have to, of course, have the mass of the Earth. Mass of Earth, and that's a huge number. It's like 10 to the 24th kilograms. Earth. And if we knew the constant, which is capital G, which I'm going to show you in here in a second, and if we also knew the distance, now remember I said that the distance is about 4,000 miles, and a mile is about 1.6 kilometers. So we're talking, around 6,400 kilometers is the radius of the Earth. So if we had 6,400 kilometers, if we plugged in these actual values, and of course the value of G, in fact, I'm going to go ahead and put the value of G in here if I can. Maybe I can't because I'm animating. But anyway, it's just a constant value, which we're going to learn about. If I multiply that G times the mass of the Earth divided by 6,400 kilometers squared, I would wind up with little g. Because notice that all I'm left with that's unknown is the mass of the person. So essentially the right equation is just a specialized instance of the equation on the left, which is a much more general equation. If you've examined the equation from the previous slide very carefully, again, that's Newton's law of universal gravitation, you will notice that gravity decreases as you get farther away from an object. In fact, it decreases as 1 over the distance squared. That's the relationship. It's an inverse relationship. So as the distance increases, the force decreases, but it never goes to 0. Even when your distance is really large, technically there is a small, tiny little force there. So if you've ever been tempted to think that the reason that astronauts appear to be weightless in space is because there's no gravity in space, think again. And you should be able to confirm this to yourself by just looking at this graph here. This graph is going to be useful in a couple of slides when I recommend that you check out the weight on other planets skill builder. So if you want to drop a few pounds, it turns out all you have to do is get a little bit farther away from the Earth's center. Just climbing Mount Everest will actually make you weigh less. Why is that? Because your mass has not changed. The mass of the Earth has not changed. However, the distance between you and the center of the Earth does increase. Like I said, the distance between the Earth and the center of the Earth's surface and the Earth's center is about 4,000 miles. Mount Everest is 5 miles high, so you would actually be 4,005 miles away from the center of the Earth when you're on the top of Mount Everest, and that will affect the gravitational force with which the Earth pulls on you. In other words, that would affect your weight. As I mentioned a couple of slides ago, this is the skill builder that I was referencing. This is the weight on other planets skill builder, and it, again, just is going to give you a chance to check out how much you might weigh on other planets, remembering that weight and mass are different. Mass is just how much stuff you're made of, and that's not going to change no matter where you're at. However, your weight will change because that's going to be the local force of gravity acting on you. So again, not a requirement, but certainly worth checking out. Okay, for whatever reason, the current edition of the book does not have a section on weight and weightlessness. It used to be in older editions, no longer there, but it's still a very, very important concept. Now think about what weight is. We just got over stating that according to the law of universal gravitation, essentially anything that has mass is going to have weight. And usually that weight is, we talk about the largest object that you're close to. So in our case, our weight comes from the fact that the Earth pulls on us with a gravitational force, and we can calculate the weight. So what does it mean to say that something is weightless then? Because we're used to talking about people in the International Space Station, or perhaps someone who is falling in an elevator that the cable has snapped. They appear to be weightless, right? And yet we know that they haven't lost mass, and therefore the Earth still is pulling on them. In fact, if the Earth wasn't pulling on them, they wouldn't be falling at all. They're falling because there's a force acting on them. That force is the Earth's pull. So why do we say weightless? And what does that really mean? What it means is that there's nothing that you're touching that is telling you that you weigh anything. We're used to walking around all day on floors, and the Earth is pulling on us, and therefore our feet apply a force to the floor, and the floor applies a force to our feet that we call the normal force of this, or the support force. And it's that normal force constantly acting on our feet that tells us, oh yeah, we weigh something. But imagine you step onto an elevator, and initially the elevator's fine, and you feel like you've got weight. You feel that force of the floor pushing on your feet, that normal force, telling you you have weight. All of a sudden the cable snaps, and the elevator starts to fall at the same rate that you are falling. So the Earth is still pulling on you. You still technically have weight. However, you don't feel like you have weight because you are no longer pushing on the floor of the elevator, and the elevator is no longer pushing on your feet. So therefore, when you're in free fall, you're not truly weightless. You feel weightless because there's nothing that you are pushing on that makes you feel like you weigh anything. Okay, these are just pretty much standard definitions of projectile motion. Have you seen projectile motion before? You bet you have. Last module, remember that Civic and Town Car question. Remember the Civic and the Town Car are being pushed across the parking lots to the edge of a cliff, and all of a sudden the pushes stopped right at the edge of the cliff. We didn't have our pushers go over the edge. They stopped pushing, and the cars went off the edge of the cliff. And what happened to them? Remember, the Civic was going faster, and it wound up landing farther away from the base of the cliff than the Town Car did. But remember, they hit at the same time. And why was that? Because the velocity, when the cars left the cliff's edge, neither one had any vertical velocity. They both had horizontal velocity. And in fact, in the absence of gravity, if we could do a Wile E. Coyote and turn off gravity, those cars would have just kept on going in the air at the same velocities that they left the cliff with, forever and ever and ever. So obviously the Civic was going faster, so it would have continued to outpace the town car, but they both would have moved strictly horizontally. That's in the absence of gravity. With gravity, what happens? Well, with gravity, the Earth starts to accelerate the cars vertically. It starts giving them vertical velocity. They initially have no velocity vertically. They start to pick up velocity vertically. And it turns out, if you remember the free fall stuff, it turns out that everything in the absence of air resistance in free fall accelerates at g. It doesn't matter whether you're a town car, doesn't matter whether you're a Civic, doesn't matter whether you're an apple or a grain of sand or a feather. You accelerate at g. So both cars would start accelerating at the same rate of acceleration. And they're going to do it over the same distance, because remember, the cliff was the same height for both of them. That's why they both spent the same amount of time in the air. So this section will kind of test you again on your projectile motion, but keep in mind when you're thinking about projectile motion, separate your velocity into x part, or a horizontal part, and a y part, a vertical part. The horizontal part will always remain constant. It's unaffected by gravity because gravity is a vertical force. Therefore, if gravity only produces a vertical acceleration, it's going to only affect the vertical velocity. Horizontally, nothing is going to change. This is illustrated on the slide if it will animate for you. If not, essentially what I'm showing here is that I've got one guy who drops a ball right off the cliff, just drops it, no horizontal velocity. The other guy throws the ball horizontally. That's very important. He's got to throw it with an initial velocity that is strictly horizontal. He doesn't want to throw it down. He doesn't want to throw it up. He's going to throw it straight out. And it turns out if he does so, just like the town car and the Civic, where the drop ball is going to be the town car, the horizontally thrown ball is going to be the Civic, they're both going to hit the ground at the same time. And notice that vertically they both move the same amount of distance every second, because again, they're both being accelerated at a rate of g. And the only difference being that the thrown ball is going to wind up landing farther from the base of the cliff than the drop ball is. The difference in this slide compared to the last one is that in this case, instead of the guy throwing the ball horizontally off the cliff, he actually throws it with a combination of both horizontal velocity and vertical velocity. He's kind of throwing it down, down into an angle. And therefore, in 5 seconds, the ball actually winds up traveling farther in the y direction than it did on the last page. But that's to be expected because he threw the ball with an initial vertical velocity, whereas when the ball is thrown horizontally, it has no initial vertical velocity. Now, if all these angles and breaking vectors into X and Y parts is new to you, I encourage you to check out this skill builder. The Trig Stuff skill builder will certainly come in handy just to show you that yes, any arrow can be broken into a horizontal part and a vertical part. And once you've understood that, then try to add them together. It turns out that when you add vectors, all you do is put the tail of the second vector onto the tip of the first, and then go from the tail of the first to the tip of the second. So you're essentially combining vectors. Get a little bit of practice with that using the Name That Vector skill builder. And then finally, I really do encourage you to check out the Monkey and the Zookeeper. Give that one a shot, and that's actually going to be the next section in this module PowerPoint. I'm going to be doing a little bit of demonstration of the Monkey and the Zookeeper. But check it out first, then watch the rest of the video. Hopefully you did the Monkey and Zookeeper skill builder yourself. If you didn't, I showed you a video before this slide of me shooting at a falling monkey. And I actually aimed high that time. You should have seen that the ball went above the monkey. I was aiming above the monkey to begin with. But the reason why I showed that one first is I wanted to actually point out this is a graph of the motion of the monkey, not the ball, but the motion of the monkey. Notice I had some blue dots. I made a motion diagram of the monkey as it fell, just to point out that if I made a position versus time graph of the motion of the monkey, I'd wind up with something like this. Notice what we got here. We've got the position, the y position, the vertical position of the monkey, and we're plotting it versus time. And so at time, now notice it's not time 0, it's about time 0.5 seconds. It's about a half a second after the clip begins when I actually pull the trigger and the ball comes flying out of the gun. And that's when the monkey starts to drop. But the monkey starts at position 0, right? We're going to call where he was hanging, that's position 0. And as time went on, notice what happened. His position became more and more negative. He was falling downward, correct? So we wind up with negative positions, and eventually about, gosh, this is 0.8 here, so about 0.86 time, it would have fallen a little more than a meter. But notice how it fell. It didn't fall. Notice what this is. This is not a diagonal line, is it? It's a curve, correct? Again, we can't forget about those position versus time graphs that we studied in the first module. Still very important. When you see a curve on a position versus time graph, what does that tell you? That tells you that the object is not moving at a constant velocity. This tells us that an object is moving at a changing velocity. So that's the big thing. We could worry about these numbers, and I did a curve fit to the data and came up with some numbers. I don't really care about that. What's important is that we understand that our monkey was falling at a changing velocity. It was accelerating. And it turns out that the acceleration was approximately g, 9.8 meters per second, which is what anything should fall, whether it's a monkey, whether it's a bullet, whether it's a feather, whether it's a brick. Everything should fall at g. Doesn't matter the mass of them if we can ignore air resistance. That's what free fall is. Okay, this is the same video again when I aimed high and shot the ball over the monkey. And what I've created here is a velocity versus time graph, again, of the monkey, not the ball, but of the monkey. Again, it's velocity versus time. And so when the monkey first dropped, it had no velocity. But then as time went on, it picked up speed. So it just picked up speed, which means that its velocity increased in the negative direction because, again, it's falling downward. And so notice that the velocity at about, let's see, whatever time this is, 0.66 seconds. And again, my clock didn't start at 0. When the photo gate first got tripped, when the monkey first started dropping, it was about 0.5 seconds into the video clip. But after a little less than 0.2 of a second, it's now going at -3 meters per second. And then sometime later, it was going even faster downward. It was going at -5 meters per second at about 0.8 seconds, or about 0.3 seconds into the clip. So notice that the speed was picking up. It was getting faster and faster in the negative direction. But notice that instead of seeing a curve here, that red line is my data and the pink line is essentially a fit. I did a linear fit to the data. So essentially my velocity versus time graph looks like a diagonal line. A diagonal line, remember the slope of a diagonal line on a velocity versus time graph is indeed acceleration. And of course, my acceleration should again be about g. So the fact that I see a curve on a position versus time graph and I see a diagonal line on a velocity versus time graph tells me that my object was accelerating. In fact, it was accelerating at 9.8 meters per second. That's the monkey. But again, remember, that's true of all objects, including the ball that I was firing at the monkey. You just watched a different video. This was me actually aiming at the monkey, and in this case, I made a motion diagram of the motion of the ball. And it made that nice parabola that we're so used to. For throwing objects, if you throw them at an angle, they're going to create a parabola. But one thing I wanted to point out is that we can break that parabolic motion into x parts and y parts. And so what I've actually got plotted here is the x position of my ball versus time. Time's on the x-axis. And so notice that at time 0, well, actually not, at time 2.4. Again, this is 2.4 seconds into the clip. I actually pulled the trigger, and that's when the ball first came out of the cannon. But the initial position was 0. And then what happened? As time went on, notice that my positions became more and more negative, which should make sense because my ball was moving from right to left across your screen. So if we called the cannon's muzzle 0, then everything to the left should be negative positions. And sure enough, that's what we're seeing here. My position was changing as time went on, but notice how it changed. It changed in a linear fashion. I see a diagonal line on a position versus time graph, which tells me what? Remember, the slope of a position versus time graph is velocity, average velocity. So my average velocity was a constant, which makes sense. Horizontally, however fast my ball was going horizontally when it was fired, that should not change during the entire flight because there is no horizontal acceleration. The acceleration involved here is strictly vertical. So horizontally, my ball should move at a constant speed the entire time. And just to prove the point, I actually plotted the horizontal velocity. That's what x velocity stands for here. The horizontal velocity versus time. Again, starting from when the ball was launched out of the cannon. And sure enough, what you see is I've got a horizontal line here for a velocity versus time graph. Remember that the slope of a velocity versus time graph gives me acceleration. But in this case, well, what's the slope of a horizontal line? 0, right? Because my ball was not accelerating horizontally. It stayed the same speed. In fact, the speed was around, the average, it was going at about -7 meters per second to the left. It was going from right to left. That's where the negative comes in. But notice that it was right around 7 the entire time. There's 7 on my y-axis. And notice that it was right around 7 the entire time. Now I took an average value, but for the most part, it was right around -7 the entire time, which meant it moved at a constant velocity, which again should be no big surprise. For parabolic motion, for projectile motion, the x value doesn't change. The x velocity never changes. It's only the vertical velocity that undergoes acceleration. Okay, so this is again the video of me firing at the monkey. This time again we are looking at the motion of the ball. We're not looking at the motion of the monkey. What we've created here is a position versus time graph for the position of the ball vertically with time. And one thing you should notice is, hey, it's a position versus time graph, and instead of it being a diagonal line, it is a curve. Just like the graph we saw of the monkey's motion, right? Didn't the monkey have a position versus time graph that looked like a curve? Except for the only difference was, for the monkey, it started up top, and it only had a kind of a half of a curve, half of an arc. Well, that's because the monkey was only going in one direction. It only dropped, it only went downward, and therefore it started with a position of 0 and just moved into the negatives. For the motion of the ball, it actually starts out at position 0, and actually, because it was fired upward, gains positive positions as time goes on until it reaches its highest point. Then it starts to fall back down toward 0, and then it actually did drop down below 0 near the end of its flight. But notice that despite the fact that the ball was moving from right to left on our video screen, on our plot, because our x-axis is time, notice that it kind of looks like it's going from left to right. That's again just because we were plotting just the y position, how high or how high above or below the launch point the ball is at every instant. And so we see this parabolic motion. I have plotted the velocity versus time graph of the ball vertically. Again, so this is y velocity versus time. And notice that, again, it resembles what the monkey did, with the exception of, remember, the monkey essentially started out with a velocity of about 0, and then its velocities became larger and larger in the negative direction. Whereas with the ball, notice I start out, when the ball is first fired, its velocity is not 0. In fact, it's a large positive velocity. The vertical velocity is large and positive when you launch it, because we're essentially shooting the ball up into the air. But again, just like if you toss a ball in the air, what happens to it? It immediately starts to get slower, and that's what we see here. It's still positive, but it gets slower and slower and slower as it's on its way up to the top of its motion. When it gets to velocity 0, that's when it's at its highest point. When its vertical velocity has become 0, that's when it's at its highest point, and then the velocities start to become negative, and it gets faster and faster negative. But one thing that you must notice is that this is a diagonal line. The slope never changes. And again, what's the slope of a velocity? What's the slope of a line on a velocity versus time graph? It is acceleration. And again, our acceleration here is right around g, around 9.8 meters per second squared. Because again, no matter what the object is, whether it's a ball, whether it's a monkey, everything should accelerate at 9.8 meters per second squared. I hope you recognize in those monkey hunter videos that in the absence of gravity, let's pretend there was no gravity, obviously I would want to aim directly at the monkey, because the ball would just go straight up toward the monkey in the absence of gravity. But with gravity, of course, the ball drops. But what's important for you to understand is that despite the fact that the ball drops, the monkey also drops. And in fact, because they're both being accelerated at the same amount, the same g, and they're being accelerated for the same amount of time, right? The amount of time is how long it takes the ball to go that distance horizontally from the gun to essentially the door there, where the door jamb, where the monkey was dropping. The amount of time is the same. The ball is crossing that distance in the same amount of time that the monkey is falling, and therefore they're both going to drop the same amount. And that's why, even with gravity, I still want to aim at the monkey. Now, when I aim too high, sure, the ball dropped, but the monkey also dropped, and because the ball wound up above the monkey. When I aim too low, same thing. The ball dropped an equal amount as the monkey did, but of course I was aiming too low, and so therefore the ball passed low of the monkey. These are all, again, examples of projectile motion. And my ball, which was shot as a projectile, went through a little parabolic path, fell to the ground each time. Why didn't it go into orbit? Well, it turns out I wasn't firing it fast enough. But if you fire something fast enough, it will go and curve around the Earth at the same curvature that the Earth is. And that's when you actually send something into orbit. There are a couple of orbits discussed in the book. Geosynchronous orbit is one where you've got a satellite placed at a sufficient distance from the Earth and going at a sufficient speed that it essentially stays in the same location over the Earth all the time. So even though it's orbiting, its orbital period is the same as the rotational period of the Earth, and therefore it stays over the same spot. This is very important for communication satellites, so you can have cell phone coverage. It's also very important for weather satellites when they're looking at hurricanes. There's a GOES east, there's a GOES west. These are satellites that stay always over the Atlantic Ocean, looking at that same area, monitoring the ocean for changes. So the geosynchronous satellites are very important in today's world. The last skill builder of this module is the one entitled Orbital Motion. What this is going to teach you is a very important lesson about how things orbit in reality. It seems like it would make sense that all things orbit in perfect circles. It turns out that they do not. Planets move in elliptical paths. An ellipse is essentially just another way of kind of saying an oval. It's an oval-shaped path. And this skill builder will give you a chance to investigate that motion. But all planets move in elliptical paths. A lot of satellites move in elliptical paths. Comets move in elliptical paths. Again, check out the skill builder. Not required, but certainly useful in some of the skills tests and live activities for this module.